By 1973, only a few young physicists were still wrestling with the obscure equations of string theory. One was John Schwarz, who was busy tackling string theory's numerous problems. Among them, a mysterious massless particle predicted by the theory but never seen in nature, and an assortment of anomalies or mathematical inconsistencies.
We spent a long time trying to fiddle with the theory. We tried all sorts of ways of making the dimension before, getting rid of these massless particles and the tachyons and so on. But it was always ugly and unconvincing.
For 4 years, Schwarz tried to tame the unruly equations of string theory, changing, adjusting, combining and recombining them in different ways. But nothing worked. On the verge of abandoning string theory, Schwarz had a brainstorm. Perhaps his equations were describing gravity, but that meant reconsidering the size of these tiny strands of energy.
We weren't thinking about gravity up till that point, but as soon as we suggested that maybe we should be dealing with a theory of gravity, we had to radically change our view of how big these strings were.
By supposing that strings were 100 billion times smaller than an atom, one of the theory's vices became a virtue. The mysterious particle John Schwarz had been trying to get rid of now appeared to be a graviton, the long sought-after particle believed to transmit gravity at the quantum level. String theory had produced the piece of the puzzle missing from the standard model. Schwarz submitted for publication his groundbreaking new theory describing how gravity works in the subatomic world.
It seemed very obvious to us that it was right, but there was really no reaction in the community whatsoever.
Once again, string theory fell on deaf ears. But Schwarz would not be deterred. He had glimpsed the Holy Grail. If strings described gravity at the quantum level, they must be the key to unifying the four forces. He was joined in this quest by one of the only other scientists willing to risk his career on strings, Michael Green.
In a sense, I think we had a quiet confidence that string theory was obviously correct, and it didn't matter much if people didn't see it at that point. They would see it down the line.
But for Green's confidence to pay off, he and Schwarz would have to confront the fact that in the early 1980s, string theory still had fatal flaws in the math, known as anomalies. An anomaly is just what it sounds like. It's something that's strange or out of place, something that doesn't belong. Now, this kind of anomaly is just weird. But mathematical anomalies can spell doom for a theory of physics. They're a little complicated, so here's a simple example. Let's say we have a theory in which these two equations describe one physical property of our universe. Now, if I solve this equation over here and I find x equals 1, and if I solve this equation over here and find x equals 2, I know my theory has anomalies because there should only be one value for x. Unless I can revise my equations to get the same value for x on both sides, the theory is dead. In the early 1980s, string theory was riddled with mathematical anomalies kind of like these, although the equations were much more complex. The future of the theory depended on ridding the equations of these fatal inconsistencies. After Schwarz and Green battled the anomalies in string theory for 5 years, their work culminated late one night in the summer of 1984.
It was widely believed that these theories must be inconsistent because of anomalies. Well, For no really good reason, I just felt that had to be wrong because I felt string theory's got to be right, therefore there can't be anomalies. So we decided we got to calculate these things.
Amazingly, it all boiled down to a single calculation. On one side of the blackboard, they got 496. And if they got the matching number on the other side, it would prove string theory was free of anomalies.
I do remember a particular moment when John Schwartz and I were talking at the blackboard and working out these numbers which had to fit, and they just had to match exactly. I remember joking with John Schwartz at that moment because there was thunder and lightning. There's a big mountain storm in Aspen at that moment. And I remember saying something like, that we must be getting pretty close because the gods are trying to prevent us completing this calculation. And indeed, they did match.
The matching numbers meant the theory was free of anomalies, and it had the mathematical depth to encompass all four forces.
So we recognized not only that the strings could describe gravity, but they could also describe the other forces. So we spoke in terms of unification, and we saw this as a possibility of realizing the dream that Einstein had expressed in his later years of unifying the different forces in some deeper framework.
We felt great. That was an extraordinary moment because we realized that no other theory had ever succeeded in doing that.
But by now, it's like crying wolf. Each time we'd done something, I figured everyone's going to be excited, and they weren't. So I figured by now I didn't expect much of a reaction.
But this time, the reaction was explosive. In less than a year, the number of string theorists leapt from just a handful to hundreds.
Up to that moment, the longest talk I'd ever given on the subject was 5 minutes at some minor conference, and then suddenly I was invited all over the world to give talks and lectures and so forth.
String theory was christened the theory of everything.